All right, this problem says a trough has ends shaped like isosceles triangles and has a length of 10 meters with 4 meters and a height of 5 meters. So let's go ahead and draw that. Okay, so I paused it real quick and got this drawing on the screen. It says water is being pumped into the trough at a rate of 6 meters cubed per minute. So water is being pumped into the trough. So that means that dV dt is 6. The volume of the trough is changing at that rate. And then it says, at what rate does the height of the water change when the water is 3 meters deep? So they're also then giving us our H equals to 3. That's the height of the water. So for clarity on this question, we should be real clear that the 5 is this height here, and we should look at this view to try to get a better idea of what's going on, knowing that this is the height. And so it says, at what rate does the height of the water change when the water is 3 meters high? So knowing that this is 5, and of course the whole thing is 4, but we might want to say that that's 2. And the 3 is going to be somewhere along this line here. Maybe we'll draw it a little cleaner than that. This is where H is 3. And so therefore, we should recognize that the volume inside the trough is given by V of t, and it's going to be, it's a triangle, so it's 1/2 length times width. So the length of the trough is 10, and then it's the width and the height of the trough. 10 is a constant, and then this piece, and this piece is the area of the triangular part. Okay, so then we can start differentiating, but not before we make a substitution for W of t, recognizing that there's a constant ratio between this, which is 2, because we've got similar triangles. 2 to 5 is going to be equal to the width or the height, or just a general, that's a generalization, because we could be talking about that width. And that height, and actually that's half of the width. And so with a little bit of algebra, we're going to go ahead and solve for h of t, for w of t rather. So let me go ahead and try to isolate the w of t. And what we're going to do, we're going to copy the left side. But we are able to multiply both sides by 2h of t, which allows us then to isolate w of t. And our final answer is that w of t is 4/5 h of t. So let's go ahead and come in here and do a substitution. Actually, let's simplify that, because that's just going to be 5. And this is 4/5. So I think in a minute, we're going to be able to simplify further. So we did this, we got 5. Then I'm replacing the w of t with this 4/5 h of t times h of t. So one more step to simplify. So it's 4 h of t squared. Now if we differentiate there, so I've got b prime t. Well, let's use a Leibniz notation since we're going to use it on the right side. So I've got dv dt is equal to 8 h of t, which is derivative of h with respect to time. And we should have said that at the beginning. This is asking for what rate does the height of water change? So that is our unknown. It's the dh dt. That's our unknown. But fortunately, shows up in that equation. And therefore, dv dt, we wrote that down, was 6. This is 8. This is 3. We're getting those from here. dh dt, and therefore dh dt is equal to 6/24, which is a quarter. And that's how we do this problem.